Welcome back. In this module, we are going to discuss about algorithms. Since computer cannot do anything on its own, it must be instructed to do a desired job. Hence, it is necessary to specify a sequence of instructions that a computer must perform to solve a problem. Such a sequence of instructions written in a language that can be understood by a computer is called a computer program. To produce an effective computer program, the programmer must first plan the logic or the various steps of the program. There are certain standard tools available to assist the programmer in designing the program logic. The most commonly used logic designing tools are algorithm and flowcharts. Algorithm. The word algorithm comes from the name of the 9th century Persian mathematician Abu Abdullah Muhammad bin Musa al-Khwarizmi. The word algorithm originally referred to the rules for performing arithmetic using Arabic numerals, but evolved into algorithm to include all definite procedures for solving problems or performing tasks. The term algorithm may be defined as an ordered set of unambiguous executable steps which define a terminating process. In order to qualify as an algorithm, a sequence of instructions should possess the following characteristics. Each and every instruction should be precise and unambiguous. Each instruction should be such that it can be performed in a finite time. One or more instructions should not be repeated infinitely, as the algorithm has to be terminated ultimately. An algorithm may have 0 or more inputs which are externally supplied. After performing the instructions, that is, after the termination of algorithm, the desired results should be obtained. Categorizing algorithm. To discuss algorithm complexity, mathematicians categorize algorithm as either tractable or intractable. Tractable problems. These problems, which are fast, efficient and easy, have a runtime that grows at a slow rate when compared to the input size. Technically, a tractable problem is one where the time equation is a polynomial function of the input size. A tractable problem can be solved in a reasonable amount of time or with a reasonable amount of computer resources. Intractable problems. These problems, which are slow, inefficient or hard, have a runtime that grows rapidly when compared to the input size. An intractable problem has a time equation that is an exponential function of the input size. These types of problems take lot of time or huge amount of resources to reach a solution, and sometimes it cannot be solved. Algorithm representation. There are certain issues relating to an algorithm's representation. Here we are trying to establish a representation system for our use. Primitives. The representation of an algorithm requires some form of language. For humans, this might be a traditional natural language like English or the language of pictures. But if the terminology used has more than one meaning, these may lead to misunderstandings. Communication problems arise over misunderstanding regarding the level of details required. In short, if the language used for an algorithm's representation is not precisely defined, there arise communication problems. Computer science approaches these problems by establishing a well-defined set of building blocks called primitives. Use of primitives remove the problems of ambiguity and establishes a uniform level of detail. A collection of primitives along with a collection of rules stating how the primitives can be combined to represent more complex ideas constitute a programming language. Each primitive has two parts such as syntax and semantics. Syntax refers to the symbolic representation and semantics refers to the meaning of the primitive. If an algorithm is expressed in terms of the individual machine level instructions, it will be easy for the machine to execute. Since it is tedious to prepare algorithm in terms of machine instructions, we normally use a collection of higher level primitives such as pseudocode or the high level programming languages. There are many ways in which an algorithm can be expressed. The four common options are English, pseudocode, a real programming language, and flowchart. English is the most natural but least precise language. The real programming languages like C are precise but difficult to write and understand. Pseudocode is useful because it is a suitable medium. It is an outline of a program which is written in a form that can easily be converted into real programming statements. Pseudocode can neither be compiled nor executed. Also, there are no real formatting or syntax rules. Pseudocode is also called Program Design Language or PDL. One way to obtain the pseudocode is simply to loosen the rules of the formal language in which the final version of the algorithm is to be expressed. This approach is used when the target programming language is known in advance. Pseudocode is made up of the following logic structures that have been proved to be sufficient for writing any computer program. Sequence logic. It is used to perform instructions in a sequence, that is, one after the other. Thus, for sequence logic, pseudocode instructions are written in an order in which they are to be performed. The logic flow is from top to bottom. Selection logic. It is also known as decision logic. It is used for making decisions and for selecting the proper path out of two or more alternative paths in the program logic. Selection logic is depicted as either an if-then or an if-then-else structure. Iteration logic. It is used to produce loops when one or more instructions may be executed several times depending on some of the conditions. It uses two structures called the do-while and repeat until. For example, computing sales tax. Pseudocode the task of computing the final price of an item after figuring in sale tax. The procedure is: first, get price of an item, get sales tax rate. Sales tax equal to price of item into sales tax rate. Final price equal to price of item plus sales tax. Display final price. Halt. Variables: price of item, sales tax rate, sales tax, final price. Here, the operations are numbered and each operation is unambiguous and effectively computable. Also, extract and list all variables used in the pseudocode. This will be useful when translating pseudocodes into a programming language. The purpose of the pseudocode is to provide a means of representing algorithm in a readable, informal manner. The flowchart is a means of visually presenting the flow of data through an information processing system, the operations performed within the system, and the sequence in which they are performed. The flowchart is drawn according to defined rules and using standard flowchart symbols prescribed by the American National Standard Institute or ANSI. Some standard flowchart symbols which are frequently required are shown here. Algorithm discovery. The program development consists of two activities: discovering the underlying algorithm and representing that algorithm as a program. Discovery of algorithm is usually a challenging step in software development process. The technique of problem solving and the need to learn more about them are pertinent to almost any field. The close association between the process of algorithm discovery and that of general problem solving has caused computer scientists to join with those of other disciplines in the search for better problem solving technique. The ability to solve problems remain more of an artistic skill to be developed than a precise science to be learnt. The mathematician G. Polya in 1945 defined problem solving phases as below. Phase 1, understand the problem. Phase 2, devise a plan for solving the problem. Phase 3, carry out the plan. Phase 4, evaluate the solution for accuracy and for its potential as a tool for solving other problems. In the context of program development, these phases can become phase 1, understand the problem, phase 2, get an idea of how an algorithmic procedure might solve the problem, phase 3, formulate the algorithm and represent it as a program, phase 4, evaluate the program for accuracy and for its potential as a tool for solving other problems. Another approach is stepwise refinement, which is essentially the technique of not trying to conquer an entire task at once. Stepwise refinement views the problem at hand in terms of several sub-problems. The idea is that by breaking the original problem into sub-problems and then solves the entire problem by solving a collection of easily solved sub-problems. It is a top-down methodology which often guided by the problem solver's intuition, which might be working in a bottom-up mode. Hence, the algorithm discovery remains a challenging art that must be developed over a period of time rather than taught as a subject consisting of well-defined methodologies. Iterative structure. As mentioned earlier, iterative structures are used in algorithms to describe the repetitive structure. Some popular algorithms like sequential search and the insertion sort is briefly discussed here. The sequential search algorithm. To search for the occurrence of a value in a list, we need to construct an algorithm. The algorithm determines whether that value is in the list. If it is there, the search is considered to be success, else failure. We assume that the list is sorted according to some rule for ordering its entries. We might scan the list from its beginning, comparing each entry with the target value. If we get a match, the search terminates as a success. If we reach the end of the list without finding the target value, the search terminates as a failure. In pseudocode, this process can be represented as: select the first entry in the list as test entry, while target value greater than test entry and there remain entries to be considered, do select the next entry in the list as test entry. Upon terminating this while structure, one of the two conditions will be true. Either the target value has been found or the target value is not in the list. In either case, we can detect a successful search. If the target value and the test entry are equal, the search has been successful. Thus, we can add to the end of the pseudocode routine the statements: if target value equal to test entry, then declare the search a success, else declare the search a failure, and if. This sequential search algorithm can be expressed in pseudocode as below. Procedure search. The arguments list target value. If list empty, then declare search a failure, else select the first entry in the list as test entry. While target value greater than test entry and there remain entries to be considered, do select the next entry in the list as test entry. If target value equal to test entry, then declare the search a success, else declare the search a failure, and if. Loop control. The repetitive use of an instruction or sequence of instructions is an important algorithmic concept. This iterative structure can be implemented by loop, in which a collection of instructions called the body of the loop is executed repeatedly under the direction of some control process. The use of loop structure produces a higher degree of flexibility than would be obtained by explicitly writing the body several times. The control of a loop consists of these activities: initialize, test and modify, with the presence of each being required for successful loop control. The test activity causes the termination of the loop by watching for a condition that indicates the termination. This condition is known as the termination condition. The other two activities in the loop control ensures that the termination condition will occur. The initialization step establishes a starting condition and the modification step leads this condition toward the termination condition. Recursive structure. Recursive structure provides an alternative to the loop for implementing the repetition of activities. Recursion involves repeating the set of instructions as a subtask of itself. Binary search. This is the way of searching a dictionary. In this case, we cannot perform a sequential entry by entry search. Here, we do have a prior knowledge of where words are likely to be found. We normally start the search with the middle entry in the list. If the middle entry in the list is the target value, we can declare the search as a success one. Otherwise, we can restrict the search process to the first or last half of the list depending on whether the target value is less than or greater than the entry. To search the remaining portion of the list, the same approach can be followed. That is, start with the middle entry in the part. If it is the target value, the search is success. Otherwise, we can restrict the search to an even smaller portion of the list. The binary search algorithm in pseudocode can be viewed as follows. Procedure search, arguments list and target value. If list empty, then report that the search failed. Else, select the middle entry in the list to be test entry. Execute the block of instructions below that is associated with the appropriate case. Case 1. Target value equal to test entry. Report that the search is success. Case 2. Target value less than test entry. Apply the procedure search to see if target value is in the portion of the list preceding test entry and report the result of that search. Case 3. Target value greater than test entry. Search the portion of the list following test entry for target value and report the result of that search. End if. This process repeatedly divides the list in question into two smaller pieces in such a way that the remaining search can be restricted to only one of these pieces. This divide by two approach is the reason for the name binary search. Recursive control. The binary search algorithm is similar to the sequential search but has a significant difference. The sequential search involves a circular form of repetition, but the binary search executes each stage of the repetition as a subtask of the previous stage. This is called recursion. Just like a loop control, recursive systems are dependent on testing for a termination condition and on a design that ensures this condition will be reached. Proper recursive control involves the same three activities: initialization, modification and test for termination. Both loop and recursive control structures are ways to cause the repetition of a set of instructions, and both are equal in terms of computing power, efficiency and correctness. Algorithmic efficiency relates to how much of various resources it consumes. The goal is to reduce the resource consumption to an optimum level. The two most frequently used and measurable metrics of an algorithm are speed or running time, that is the time it takes for an algorithm to complete, and space, the memory or non-volatile storage used by the algorithm during its operation. Measuring an algorithm's efficiency is important because the choice of an algorithm for a given application often has a great impact. An estimate of the speed of an algorithm can be determined in various ways. Although the efficient use of both time and space is important, inexpensive memory has reduced the significance of space efficiency. Thus, we will focus primarily on time efficiency. The most common method used for measuring time efficiency is time complexity to determine the big O of an algorithm. The time complexity of an algorithm indicates the amount of time taken by an algorithm to run as a function of the size of the input to the problem. The time complexity of an algorithm expressed as big O notation suppresses multiplicative constants and lower order terms. When expressed in this way, the time complexity is said to be described asymptotically, that is, as the input size goes to infinity. For example, if the time required by an algorithm on all inputs of size n is at most 3n cube plus 2n, the asymptotic time complexity is O of n cube. Time complexity is commonly estimated by counting the number of operations performed by the algorithm, where an elementary operation takes a fixed amount of time to perform. Thus, the amount of time taken and the number of elementary operations performed by the algorithm differ by some constant factor. The commonly used measure of time complexity is the worst case time complexity, because an algorithm may take different amount of time for inputs of the same size. It is denoted as T of n and is the maximum amount of time taken on any input of size n. Time complexities are classified by the nature of the function T of n. For instance, an algorithm with T of n equal to O of n is called a linear time algorithm, and an algorithm with T of n equal to O of 2n is said to be an exponential time algorithm. Software verification is a broader and more complex discipline of software engineering, whose goal is to assure that software fully satisfies all the expected requirements. Dynamic verification, also known as test or experimentation, which is good for finding bugs. Static verification, also known as analysis, which is useful for proving correctness of a program, although it may result in false positives. This module gives an overview of the logical specification of the given problem solution. This is known as algorithm, and different methods for representing algorithm are discussed here. The algorithm is categorized according to the complexity as tractable and intractable. Different logical constructs such as iterative control and loop control are discussed here. The module concludes by mentioning the way to analyze the algorithm based on time and space complexities. Please try to answer the following questions. Describe how the use of primitives helps remove ambiguities in an algorithm representation. What is the difference between a formal programming language and a pseudocode? What is the difference between syntax and semantics? What are the different methods used to express an algorithm? What is meant by algorithm discovery? What are the different logic structures used in pseudocode? Design an algorithm to find all the factors of a positive number. Books for your reference. J. Glenn Brookshire, Computer Science, an Overview, 10th edition, Addison Wesley. Robert Laffo, Object Oriented Programming in C++, 3rd edition, Galcotia Publications. Stanley B. Lipman and Josie LaJoie, C++ Primer, 3rd edition, Addison Wesley. Hope you all enjoyed this session. See you next time. Until then, bye.